that this series converges if only if T is no more than the inverse of the spectral radius of the weighted adjacency matrix. So in our example, if we take T equal to 1, then the series is infinite. And if we take 0.4, then the series converges and we have some proximity measure which is minimum for the vertices 1 and 5 and maximum for vertices 2 and 2. So 2 and 2 have the strongest connection between the pairs of vertices. And this T can be interpreted as the proportion of counting shorter and longer walks in the graph. It can be shown that this measure is also a transitional measure. So it's the fourth transitional measure. More exactly, a fourth class of transitional measure because each class has a 3-parameter. Now it's called T. And we can check that the bottleneck identity is satisfied for this measure. So maybe all proximity measures are transitional measures. The answer is not, of course, because even the path measure is not transitional measure for large enough alpha. And another negative example is the communicability measure proposed by Ernest Estrada. So this property, in fact, is not very typical. And recall our question, is there any connection between transitional measures and cut point additive distances? The answer is the central theorem. In fact, it's not very difficult. It says that if we have a transitional measure, then this transformation, which can be called the logarithmic cosine transform, takes it to a cut point additive distance. And as an immediate corollary, we obtain that the walk weights, path weights, weights of spanning forests, and connection reliability produced cut point additive metrics by applying the logarithmic cosine transform. So the logarithmic cosine transform takes all transitional measures to cut point additive distances. Now let's consider the properties of one of the families. It's the family of walk distances. Maybe it's the most interesting family. First consider an example with T equal to 0.3. We see that the loop really matter, and we obtain different distances for all pairs of adjacent vertices, and the smallest distance is between 2 and 4, and the largest one is between 4 and 5, and the same situation for the pairs of vertices on the ordinary distance too. So this measure is very sensitive. And it's easy to check that the cut point additivity is satisfied for this. For example, for vertices 1, 2, and 3, the sum of two distances is equal to the third distance. Now consider some representations. The first one is a topological representation in terms of so-called commute cycles. It's a very simple representation, but what is not very good is that logarithm survives in this representation because we understand what is the weight of some structure, but we don't understand what is the logarithm of the weight. Another representation obtained jointly with Michel Desargues is without logarithm, but it involves many structures, circuits, alternating routes, other figures, and so on. And all of them make sense, but it's this theorem is not very easy to prove. The second representation is a matrix representation of the walk distance. And for some purposes, it's convenient to consider reparametrization, to take another parameter alpha instead of our parameter t, and alpha ranges from 0 to infinity, and to apply additionally a scaling factor theta, which adjusts the asymptotic properties. So the asymptotic properties are as follows. As alpha, the parameter, goes to 0, we obtain simply the shortest path distance. When alpha tends to the infinity, then we obtain some new distance. It's called long walk distance. It has such a representation in matrix terms and a topological representation in terms of weights of specific cycles. And how does it work on the simplest graphs? Consider P4 path graph. It turns out that in the sense of this distance, 2 and 3 are closer to each other than 2 and 1, exactly the golden ratio times. And in P5, 2 and 3 are closer to each other than 2 and 1, 2 times. Consider P4 with heavy ends. We take the weight of square root of 2 on the ends. And in this case, we obtain uniform distances for the adjacent vertices, 0.75. And the same thing for P5. If we take the weight square root of 2, then the distance is uniform and equal to 0.8. And the same for all paths. 5 minutes? Okay. And so the square root of 2 compensates the extremality of the terminal vertices. If we apply square root of 2 on the ends, then the structure becomes uniform in irrespective to the length of the structure. Now, as we remember, the walk distance generalizes the shortest path distance. But what is more interesting is the weighted shortest path distance. Can we generalize it too? This leads us to another family which can be considered as an improved family. Is the family of E walk distance. E because of exponential. In fact, we apply such a transformation of the edge weights. It's closely connected to the Boltzmann distribution. And we apply the same constructor, and we obtain another family with the weighted shortest path distance on one end, some new distance on the second end. We call it long E-walk distance. We obtain topological representation for it, and if we apply a special form of the normalizing factor, then the long E-walk distance coincides with the long walk distance. So we have obtained a good family, which is the weighted shortest path on one end and long walk on the other end. And it turns out that one more family, logarithmic forest distance, can be, even with arbitrary transformation of aid weights, can be represented via the walk distance by means of some procedure which is balancing. What is balancing? Balancing is adding loops, such loops that make the weight degrees equal. We have different loops, and now all the vertices have the same degree. And if we want to obtain the resistance distance from the long walk distance, we should apply the same balance. And we can obtain vice versa, the long walk distance from the resistance distance by another transformation, more complex transformation. And there are simple formulas for the long walk distance. One of them in terms of the matrix L prime, and it's actually easy to compute the generalized inverse of the Laplacian matrix here, which is shown in this remark. And even more simple formulas was obtained jointly with Babat and Galai in terms of the so-called Laplacian matrix, which is rho I minus 1, where rho is the spectral radius. So this picture shows the cut point additive distance with the shorter distance in the center for walk distance and longer distance in the center for the logarithmic forest distance. And we have not cut point additive distances here: forest, square rooted resistance, communicability distance, and plane walk distance with various parameters. In fact, they produce a distance preserves multi-lines in three-dimensional space, and here we have projections to the plane. And are the distances needed, in fact, in addition to the shortest path and resistance distance? I think the reply is yes, because, for example, there are different groups that do machine learning, cluster analysis, pattern recognition, and semi-supervised learning, and both families obtain the same result in the words of the second group, that the resistance distance does not take into account the structure of the graph, and so its use in the situation of many dimensions is strongly discouraged. And so we may conclude there is a strong demand for alternative graph distance. And several problems are as follows. First, consider the family of p resistances, study links of e distances with some physical models involving entropy, free energy, and so on. Apply these new families in the cluster analysis, and the last one, and most mathematical one, to study connections of the new distance with the Ricci curvature.
Olivevich.
Yes, on graphs. Thank you.